well as pressure and volume, and I get Boyle's law. Okay, if pressure and moles are constant, you get Charles' law. Okay, and if you have pressure and temperature that are constant, that's kind of hard for me to block this out, but you get V over N on both sides, and that would be Avogadro's law. So whenever a variable is not mentioned in a problem, you can consider it to be constant, and you have one or more of the isolated gas laws. So here's the question. Do you have to memorize Boyle's, Charles, and Avogadro's law, or can you just use this one equation and work from that? And the answer is the latter. This is all you really need to know for any physical change for a gas. Okay, if any one of these variables are constant, they just get eliminated from the equation. So like in these examples we've just done, there was no mention of the moles changing, so we just didn't have that in the combined gas law, but it's there, we just eliminated it because it's constant. Right, if N1 and N2 are the same, multiplying over N2 up top here just cancels this into unity. Okay, N2 over N1 is just 1 at that point. So that really the only equation you need to know is that bottom equation there. Okay, so when no reaction is occurring, this is when you use that equation, when only a physical change happens. Also related to STP, or standard conditions, is something called the standard molar volume. So for any mole of gas at standard conditions, okay, the volume of that gas will always be 22.41 liters. But this is for an ideal gas. So we're still dealing with ideal situations here. But for any gas, it could be xenon, it could be helium, it could be methane, all right, any kind of gas. All right, if it's an STP and it's assumed to be an ideal gas, it will always have a volume of 22.41 liters for 1 mole of that gas. And you can relate this to the molar mass of a gas using the standard molar volume. So here's a sample problem. What's the molar mass of a gas with the density of 1.2 gram per liter at STP? Okay, how do you get to the molar mass of a gas? What are the units of molar mass? Yeah, grams per mole, right? So we have a density with grams per liter, and we have a standard molar volume that relates liters to moles. I'm sure you can see how this could be a pretty easy conversion at this point. Okay, so using these two conversions, get from 1.2 gram per liter to gram per mole. What do we do? What do we multiply this number by to get it to grams per mole? Well, we want to cancel. We want to keep the grams. We want to get rid of the liters, right? So how do we do that? Yeah, 22.41 on top. Liters will cancel, and you'll end up with units of grams per mole for your molar mass. Right, so that comes out to be 27. Right into 2 sig figs, of course. What if you wanted to go the other way? What is the density of the gas that has a molar mass of 121 gram per mole? Okay, at STP. So what if we had 121 grams over moles? What do we multiply by? And now it's 1 over the molar volume. So 1 mole over 22.41 liters. And so now I've got grams per liter again, which is a density unit. So you might be confused and say, oh, well, if it says STP, I gotta use 1 atmosphere and I gotta use 273 Kelvin. But really, it's just asking if it's relating molar mass, just think of the standard molar volume. Okay, questions there? This is stuff that you probably should have seen in one of those sections, but maybe I forgot. So combining all the ideal gas laws, okay, Boyle's, Charles, Avogadro's, okay, and you combine it all, okay, so this K constant stays the same, P is on the bottom here because it's on the bottom from Boyle's law. You get K times NT over P. This K changes into a capital R, okay, and you get the ideal gas law from that. So if you multiply P up here and you change this K into an R, this is what you get. So I just sort of derived the ideal gas law for you. And that R, do you remember what the R constant is? 0.08206 liters atmospheres per mole Kelvin. And you'll even get this on the exam, right? You don't have to memorize this, right? Just, you know, but just showing you where it came from. So at standard conditions and using the standard molar volume, okay, you get the gas law from that. All right. So using PV equals nRT, let's do one example of that. What's the temperature of 67.4 grams of, I believe that comment is on nitrous oxide. That's the laughing gas. Okay, NTO. So 67.4 grams of nitrous oxide, okay, at 5.00 atmospheres in a 7.00 liter container. What would be the temperature of that gas? So to find the temperature from the ideal gas law, solving PV equals nRT for temp, what do we get? We get PV over NR. I can't begin to say how many times I've seen students do this. I've seen that so many times, it's like, what are you doing? So just, know that you just divide over. I don't know how that happens, I really don't, but maybe it's just exam jitters, I don't know. But the key to doing well on exams is to be relaxed, if at all possible. So, I promise not to like hover over you while you're taking the exam, I used to have a professor who did that kind of hover over you, watch what you're doing. It's so nerve-wracking. Okay, so doing the math, it's just PV over NR, and then you plug in the numbers here. We get, let's see, P is 5 atmospheres, and we have a volume of 7.00 liters, and then we have our moles. How do we get our moles? Yeah, so it gave us a mass of the gas, so it's just 67.4 grams divided by the molar mass of N2O, which is going to be 44.02, and then times the constant R is okay, so the moles are going to cancel, the grams will cancel, the atmospheres will cancel. The liters will also cancel. The only unit left is the Kelvin. But the Kelvin is in the denominator of the denominator, which means it's the same as being in the numerator. So plugging and chugging, that gives you 279 Kelvin.
I have 10 minutes.
All right, pretty easy. Not too bad. Why is the answer 3 sig figs? Well, because 67.4 had 3 sig figs in it, and all the others had 3 sig figs. Okay, questions about using the ideal gas law. So when do you use the ideal gas law? I think that's always a question when it comes to, excuse me, when it comes to chemistry problems. It's like, well, when do you use what equation when? You know, that's always an issue, right? So is a physical change happening here? Is a chemical change happening here? So really, right now, no change is happening. We use the ideal gas law for just calculating a parameter of a gas at rest. Okay, the gas is just sitting there. It's in this container at this temperature at a given volume. So we only use the ideal gas law when we're calculating a static condition for a gas. So that we have two equations really from this chapter so far, which really isn't really a lot. The combined gas law, or Char-Boyle-Avogadro, as I call it, that's for a physical change in a gas. And then we have the ideal gas law, which is just calculating a parameter for a gas at rest, when it's just sitting there in a container. Now, the ideal gas law is oftentimes used to calculate the amount of gas before it reacts, and it's also used to calculate the amount of gas after it reacts. So what do you do during the change? Well, usually that involves stoichiometry of some kind or another, whether it's limiting reactant or not. But that's where the ideal gas law comes into those problems. But in the meantime, just know ideal gas law, gas at rest. Okay, moving on to gas mixtures now. Okay, and this term is always seems kind of fancy, but it's not much. So Dalton, back in the 1800s, discovered that if you take a gas mixture, all of the individual pressures of that gas mixture, man, driving me crazy. So if you take a gas mixture, all the individual pressures of each gas can be additive and to form the total pressure of the mixture. Okay, so partial pressure, you can think of it as the individual pressure of a gas within a mixture. Okay, and then Dalton's law says that all of the partial pressures add up to give you the total pressure of the mixture. All right, the total pressure of a gas mixture is the sum of the partial pressures for each gas. So when they say partial pressure, it sounds really complicated, but really it's just what is the pressure of an individual gas within a mixture of gases. All right, that's all it is. And a mathematical statement of this is just P total is equal to the partial pressure of gas 1 plus the partial pressure of gas 2 plus the partial pressure of gas 3 plus the partial pressure of gas 4, and on and on and on if there were more gases. So that P1 and P2 and P3, if I read, I would just write in your notes there, partial pressure, not just P, but just, you know, P1 equals partial pressure of gas 1, and so forth, just to remind yourself. Here's a picture sort of showing this. If you took a container with helium at 2 atmospheres, and another container, another gas tank with argon at 4 atmospheres, and if you filled them up into the same cylinder, then the total pressure would become 6, because you're just adding P1 and P2 together to give you P total. So P total would be 6, P1 would be 2, P2 would be 4, and that's all partial pressures. What about air? Okay, a couple of you came to me about the pre-lecture assignment, which had to do, one question had to do with this. So air is a mixture of gases, including nitrogen, oxygen, carbon dioxide, argon, other trace gases, and water. What is the percentage of nitrogen? So here we got the percentage, partial pressures in millimeter mercury. What's the percentage of nitrogen in the atmosphere? You should just know this by heart. You just should. If you were looking for a planet to inhabit other than Earth, okay, which, let's face it, we're kind of outgrowing our planet, you know, we're like on top of each other at this point. We got to probably get to Mars first before we get to some other more inhabitable planet. What composition of Mars, what would we want to change Mars to make it livable for us? If we could just walk outside Mars and just walk around and breathe okay. What percentage of nitrogen might we want?
We have no idea.
You have no idea? Oh. So nitrogen is our balance gas in the atmosphere. It's 78%. Right? 78% nitrogen. What is the oxygen content? All right, you're killing me. It's 21% oxygen, right? So you should be looking for these percentages in the atmosphere if you were going to inhabit another planet, or make it that way. Have any of you ever seen the movie Total Recall, the original one with Arnold Schwarzenegger? If you've never seen it, the original one, don't look at the remakes. You know, that's never good. But Arnold Schwarzenegger, back around 30 years ago, when he was kind of the stud in the movie industry, he did a movie called Total Recall, and it was about a double agent who has to go to Mars to save his girlfriend. So in Mars, they've got this like big sort of city under a dome, and you can't shoot people inside the city because a bullet might puncture the glass and ruin everything, right? So they got a couple of scenes where Schwarzenegger's getting shot at, and the bullets are hitting metal framework of the building and not hitting the glass, and the guy's like, "Don't shoot! You're gonna break the dome, right?" And then it turns out there is an ancient alien hub underneath the surface of Mars, and if you put your hand like this on it, it like changes. It activates this reactor, and it shoots all of this, I don't know, oxygen and nitrogen gas in the atmosphere somehow. Maybe it's, I don't know what it's doing, but the chemistry is suspect, but the movie's really good. But anyway, and so that whole thing now, all of a sudden we see storm clouds and water's coming down, because obviously they always talk about water content on Mars, like, oh, where's the water? And it's buried deep underneath Earth or Mars crust. So we need water along with nitrogen and oxygen. On the other hand, the reality is Mars has a huge concentration of carbon dioxide in the air. When you look at when you look at Mars in the telescope, you might see poles with what appears to be ice at the poles, but that's not frozen water, that's frozen carbon dioxide. It's so cold, poles. So really it's dry ice. You say, oh, that dry ice looks so scrumptious, and then you go to drink it, and it just turns into gas when you melt it. So, but they have found evidence of water on Mars, so maybe there's hope. We have trace gases too. We've got carbon dioxide in our atmosphere, but it's a trace gas. Argon. They use argon in double pane windows as a balance gas, and it's got a nice heat capacity to it that absorbs or retains heat. What they don't mention here are all the other pollutants that are in there too, but those are trace gases as well. All right, yeah, they don't have the ozone in there. Tropospheric air quality here in the city has a lot of other stuff. Okay, so percentage-wise, okay, so how did they get this 594 here? Where does that come from? Well, if I take 0.782 times 760, what does that give me? 594. All right, if I took 0.210 times 760, what would I get? 160. So these, if you take the percentage of 760 millimeter mercury, which is the atmospheric pressure, you would get these partial pressures. All right, so the partial pressure of nitrogen gas is 594. Partial pressure of oxygen gas in the atmosphere is 160. Okay, so the partial pressure. Now, what if you were given a partial pressure, but you wanted to get a percentage of the gas? Well, if you took 594 divided by 760 times 100, you would get the percentage of nitrogen. Okay, so I would say look at this slide, and in a sense, it's important only from the standpoint it gets you thinking, well, what is partial pressure? All right, it's a fraction of the gas pressure in the mixture, which in our case is the atmosphere, which is a mixture of lots of gases. Okay, so any questions about what partial pressure is? Okay. Here's just an example. Anyone put scuba diving in here? Anyone like into the ocean and scuba diving? Occasionally I get a student who's really into scuba diving. I used to have a student who he probably dived once a week. I wish he would have studied more for my class instead of going scuba diving every weekend. But that's what he was into. So, but in a way, he brought something to the class that most people don't. That he had a lot of diving experience, and we could talk about scuba tanks. So here's an example of scuba tanks. Mixture of a scuba tank contains helium and oxygen gas combined to form a total pressure of 7.00 atm. If the pressure of the oxygen alone is 1140 millimeter mercury, what would be the partial pressure of the helium then? So this is a pretty easy problem, but you just gotta look at the units. So what might be a starting place to do this? Convert what to what? So I could do I could convert the ATMs to millimeter mercury, or I could convert the millimeter mercury to ATM. I'm going to convert the millimeter mercury to ATM. So partial pressure of oxygen, and usually they express it as like P and then O2, all right, versus P helium, which it's asking us for. So P, partial pressure of oxygen, 1140 millimeter mercury. How do we get to atmospheres from there? Yeah, divide by 760. All right, that should come out to be around 1.5 atmospheres. So if P total is equal to partial pressure of oxygen plus the partial pressure of helium, that's our statement of Dalton's law of partial pressures. And we know that P total is 7 atmospheres. And 5, oops, did I say 5? I meant 1.5. All right, pretty easy problem from here, right? So what's the partial pressure of helium? It's going to be 5.50, right? So 5.50. So how many, some of you may know this, if I dive down 30 meters into the ocean, how many extra atmospheres of pressure do I have on my chest? Actually, I'm sorry, it's not 30 meters, I think it's 10 meters. So for every 10 meters I dive down, basically every 30 feet I dive down, I have an extra atmosphere of pressure on my chest. So when they make scuba tanks, they use helium, not nitrogen, to balance out the tank in terms of pressure. And that's because the helium has a better conductivity What we mean by that is that the gas flows more quickly through tubing and whatnot versus nitrogen, which is a heavier gas, so it has a slightly more resistance to flow. So they use helium to balance out the oxygen in scuba tanks for that reason. And what that allows to happen is, as you're diving deeper, the valve, as it changes to accommodate the extra pressure on your chest, will change, and then the gas can flow faster and adjust to that faster. If you dove down 60 feet from the surface, that'd be like having 3 atmospheres of pressure on your chest. So they have to have that scuba tank has to be pressurized to a really high pressure to force your lungs to be able to expand against that pressure, that wall of water on your chest now. And then conversely, as you dive back up, you got to go slowly. Okay, if you go up too fast, what happens? And you have the possibility of getting the bends, right? You ever seen the movie The Abyss? No, it's an old movie. It wasn't very good. It's like probably 30 years ago now. But there has a scene of a guy like who went up way too fast. And he was a villain though, so he didn't really care. He's a bad guy, but he went up too fast and his I don't know. He's like lungs exploded out of his, you know, or it was really gruesome. But it was chemistry, so okay. All right, so yeah, scuba diving, pressure regulation, helium is a nice balanced gas. Now, here's something that will be new for you. We also talk about mole fractions in gas mixtures. Okay, so in a gas mixture, if I have one gas within a mixture of gases, if I just took the partial pressure of gas A over P total, okay, we're saying that that's equal to the mole fraction of the gas as well. Well, let's see how that works. We know that pressure is equal to nRT over V. So everyone all right with this? So it's, you know, P is equal to nRT over V, all right, from the ideal gas law. Is the volume that the total mixture occupies the same as the volume that the individual gas occupies? It's a gas mixture, they're in the same container, so do they occupy the same volume?
Yeah.
Yes, right? Like let's just say I'm a gas, you're a gas, you're a gas, you're a gas. Everybody in the room is their own unique gas. That's kind of disturbing to think about. We all have unique gas. Okay, but we're all in the same room. Okay, my partial pressure occupies the same volume of space as your partial pressure does. So for that reason, we can say that volume of gas A and volume of the total mixture are the same, and therefore they cancel each other out. Okay, it's dividing by those two just gives me 1. Okay. If we're in the same room together, are we feeling the same temperature? Right? Is the temperature different where I'm standing versus where you're standing? Not really, right? We have a uniform temperature in the room. For that same reason, we can say that the temperature experienced by gas A versus the temperature of the total mixture is also the same, and those cancel each other out. The constant R is the same always, no matter what, so that also cancels. So can you see now how the partial pressure fraction to the total is the same as the mole fraction of the partial gas A to the total? All right, mole fraction is equal to the pressure fraction for that reason. Can you see that? So from this, all this canceling out, we say, you know, moles of gas A divided by total moles is going to be the same fraction as the partial pressure fraction. And that's where this comes from. I have your C problem solving hand now. There'll be some problems with that aspect of it. Okay. So using that idea, let's do the sample problem. A chamber is mixed with 6.7 moles of O2 gas and 9.2 moles of helium gas, the total pressure of the gas